Okay, today we're very happy to have Ronak Soni, who's going to tell us about boundary description of the microstates of the non-supersymmetric two-dimensional black hole. Take it away.
Thanks a lot. Thanks a lot for the opportunity to speak, and especially at the last minute. I know it must have been hard, and I appreciate it a lot. So I'm going to talk about this paper that came out last week, along with the paper of Panos and Olgas, with Amar, Alex, and Krish, who are pictured in order. Amar is a postdoc in Cambridge, and he's applying this year, so pay attention to that. Alex is, of course, pictured next to Donald Trump, and we have Krish here. And so to start the whole thing, as we all know, black hole entropy is both amazing and annoying. It is amazing because it is a piece of UV physics you can see in the IR, just from classical gravity. It is annoying because classical gravity tells you how many states there are, but doesn't tell you what those states are. So the natural question is, okay, let's go away from classical gravity. Let's pick up a UV completion like string theory. Can we find the microstates in that? And the answer has, since 1996, we've known that the answer is yes, at least in some cases. Those cases typically have zero temperature, maximal supersymmetry, and large charge. Today, I want to talk about a case with finite temperature, no supersymmetry, and still large charge. There are some caveats, however. The caveat is that it's a very weird and finicky two-dimensional black hole. And unlike, say, Schrodinger, we don't find the microstates in a bulk description, but a dual boundary description. Okay. So let me just take a minute to talk about what it means to identify microstates, because whenever I spoke about this project, there was a lot of confusion about this. So typically the way we calculate, one of the ways to calculate black hole entropy is to calculate some Euclidean partition function, either canonical or grand canonical. I will stick to grand canonical for definiteness and because it's relevant to our context today. You do this using path integral techniques. The most common one is started by Gibbons and Hawking is you use the Euclidean on-shell gravity action. Okay, and you vary this path integral with temperature. Okay. Now, of course, this tells us only about the entropy. It doesn't tell you anything about the microstates except their energy, their charge, and any other microscopic properties. And of course, a partition function, a canonical partition function, for example, is a trace over all states in the theory. So what do we mean when we say, what are the microstates corresponding to this partition function? What we mean is that in the thermodynamic limit, there is an equivalence of ensembles that emerges. That the grand canonical partition function is usually dominated by states of a particular energy and particular charge, okay, which I've written in mathematical language here. And so this is called equivalence of ensembles because it's effectively a microcanonical ensemble with some factors. Microcanonical fixed charge ensemble with some factors. Okay. Here Z is a fugacity and e to the minus beta h, you know everything about. Good. And e to the s is, of course, the number of states that exist in this microcanonical fixed charge ensemble. Okay. So to identify microstates, we need to do two things. One is to identify the Hilbert space we are tracing over. This is already a non-trivial question when you talk about gravity. You know, because like, what is the Hilbert space of one side of a Schwarzschild black hole? We don't really have a description of this. But in our case, it will be solved by holography. So that thing is done. Secondly, we need to specify independently the e to the s dimensional subspace which dominates the ensemble. Okay, so you can't just say, okay, look at all states with the right energy and charges. That we already knew. It's not particularly interesting. So I would say that these two are the requirements for what it means to identify microstates. So, for example, a lot of really amazing work that's been done in the last 2 years in terms of n equals 4s, so super Yang mills, I would not say it corresponds to identifying microstates. Okay, This is not to denigrate their work. It's really amazing. And I'm just saying that it's a complicated system, so you can do only what you can do. What they do is really just calculate the partition function from boundary techniques. Yeah. So let me summarize our results. As you can imagine, I want to say that we are identifying microstates in a two-dimensional case. It's a very simple case, and that's why we're able to do it. So there is a two-dimensional black hole, which is a string theory background. Okay, it can be shown that the string theory is dual to some matrix quantum mechanics system. Matrix quantum mechanics is a quantum mechanics whose degrees of freedoms can be arranged into n by n matrices. And in our case, we'll take n to infinity. Kazakov and Tseytlin in 2001 wrote down two candidate free energies for the system. We will reproduce one of them, showing it to be the correct one. And we will reproduce it using a Hamiltonian calculation by analyzing the Schrodinger equation and finding the state that dominates the partition function. And the state is very interesting. It is a black hole-like state in the MQM. By black hole-like state, I mean it is a metastable bound state that evaporates slowly. We will also argue that the entropic term that KT found comes from some degeneracy that's not very interesting, and you shouldn't call it the entropy of the black hole. Yeah.
Ronak, sorry for disrupting. Perhaps for the audience, it might be useful to say that the space is asymptotically flat, not ADS, and that's why it evaporates, etc. Right? Because
I was going to get to that.
The usual holography at my
yeah. Thanks for that comment. I will. Yeah, that's definitely true, and I will harp on that further as the talk goes on. But thank you. Cool. So let's start with the review of the state. So we start with the cigar geometry. The cigar geometry is a 2D Euclidean black hole geometry. It is asymptotically flat, as Panos just pointed out, and it has temperature 2 pi r. So usually we think in terms of beta, the inverse temperature, but here you can think of beta as the circumference of a circle and r as the radius. Okay, so capital T is the time. This is the metric. I won't. You don't need to remember the metric. Just need to remember that it looks like a cigar in the Euclidean case. And this K is the square of the radius. Further, there is a dilaton, okay, which will turn up in the dynamics. The dilaton takes a maximum value here and then goes to minus infinity here. Okay. Good. And the maximum value of the dilaton will be related to the mass of the black hole. It's a 2D black hole, so things are slightly different as usual. This manifold is also a group coset, which can be written like this. Okay. Good. And it's asymptotically flat, and really the 2 pi r is the asymptotic radius of the cylinder. Good. So, sorry, that was just geometry. Now let's get to physics. Physics is that we are looking at a system of strings propagating on this geometry. The worldsheet action has a sigma model term, okay, has a dilaton term, r phi, as usual, and has a Vesu-Minovitan term. The Vesu-Minovitan term ensures that it's a CFT for all k, and it has a ghost term. Okay, so this is what rules the dynamics of strings on this background, and it's a Vesu-Minovitan theory, so it has a particular central charge. Okay, you can just put something, whatever it is. But the important thing is that a string theory worldsheet CFT needs to have zero central charge. To have zero central charge, this equals 0 becomes an equation for k, where k is the square of the radius. So we find, we find that the radius is fixed to a particular value, or the temperature is fixed to, in other words, the temperature is fixed to this value. Okay, which is an order 1 in string units. So it's a very stringy black hole of fixed temperature. However, the mass is related to the maximum value of the dilaton, and that you can vary independently of the temperature. It's a free parameter. So it's a very funny black hole. It's A, stringy, B has fixed temperature, but C has no relationship between mass and temperature. Okay. And these funny properties are why we'll be able to do anything at all in the end. Cool.
Ronak, can I ask something before?
Yeah.
So one could imagine also adding some kind of like internal shifty action, right? Or some matter
Yeah.
that propagates, and then in this more general action, you could perhaps change the.
Indeed,
rate,
that is
right?
completely right, and that is completely right, and I will address that in a minute. I think our techniques don't clearly generalize to that case, but I do think that there's something to be learned from our results. Okay, so the cigar is dual to the matrix quantum mechanics via a series of dualities. So the cigar, it's dual via what's called the Fatih-Zamolodchikov duality, which is a type of ER equals EPR duality. And I know the UBC audience will like ER equals EPR a lot, so I hope you're happy. To what's called the sine-Liouville string theory. The sine-Liouville string theory again has a sigma model bit, a dilaton bit, and this funny bit with the very fancy Z, which I will explain later. Okay, the sine-Liouville string theory is a particular limit of what's called the sine-Gordon model. The sine-Gordon model has a worldsheet. So this is a worldsheet action. So the sine-Gordon model has a worldsheet action, which is sine-Liouville plus this extra term. Okay. Now sorry. So whenever you have a Liouville term, you need one more term, because the Liouville term, as you send phi to minus infinity, the action goes to minus infinity, right? It has an instability. So you need something to, some sort of wall in the potential to ward off that instability. The difference between sine-Gordon and sine-Liouville is not simply that mu is 0, or some value of some parameter. It is or it is which term in the action is the main thing protecting you from this instability. In sine-Gordon, it's this what's called the tachyon wall. Okay, there's no time like there's nothing interesting in the time direction going on. It's just in the spatial direction there's a wall, and it's got a parameter mu. Okay, so when you take sine-Gordon, in sine-Liouville, mu is sent to 0, and this other term is what's going to protect you from the instability. So there's like a real non-trivial difference between the two. And the sine-Gordon model is dual to matrix quantum mechanics. So now let me tell you about this extra term in sine-Liouville. So the extra term in sine-Liouville is really just a fugacity for winding modes. Okay, a winding mode is a mode in the string which goes around the thermal circle. On a spherical worldsheet, you can think about it like this: that a spherical worldsheet with the insertion of one winding mode and one anti-winding mode, also called a vortex and anti-vortex, is really an embedding into target space where the vortex is like a little hole that wraps around this thermal circle. The anti-vortex is a hole that wraps around the thermal circle in the opposite way. Okay, so every spherical worldsheet needs to have an equal number of vortices and anti-vortices. And Z is the fugacity for these guys. Okay. And basically in sine-Liouville, because of the dressing factor that multiplies, because of the dressing factor here, basically there is a condensate of a lot of these guys at large negative phi. And later we will go from the grand canonical ensemble where there's a fugacity to a fixed charge ensemble where there will be k such pairs. Just remember this fancy math BBK, which will turn up again and again. Now let's quickly go to the MQM. The MQM is a matrix quantum mechanical system, with n squared degrees of freedom arranged in the matrix. This is the action. Now the point about the action is that it has a potential. This is a Euclidean action. I should have written that earlier. It has a potential which looks like an inverted harmonic oscillator. The inverted harmonic oscillator is an instability that is stabilized by this x to the 4 term, but the x to the 4 term kicks in at very large x. At small x, at order 1x, it's an inverted harmonic oscillator. Okay, because the coefficient of x to the 4 is tiny. It has a symmetry because of the trace in the action, which looks like conjugating x with the unitary. Now, the actual group will be important. So let me be a bit pedantic. So you can conjugate x with any unitary, of course. But whether you conjugate x with v or e to the I5v, where e to the I5 is just a phase, obviously x changes in the same way for both conjugations because the phase just cancels in v dagger and v. So the group is actually un mod the phase u1. This is called the projective unitary group. It's also sun mod zn. So for the n equals 2 case, pu2 is just SO3. Okay, so there's a particular representation theory for this group, and it is what turns up. Okay, the partition function we're interested in is a thermal partition function, but with some funny stuff in it. So here you have the usual path integral you'd expect for the action I wrote down. But here you have a boundary condition which says that x around the thermal circle doesn't come back to itself, but comes back to itself around with a conjugation. This is called a twist. And then you integrate over the twist with some potential for the trace of omega. And that potential, the parameter of that potential is this ZB. This ZB is a fugacity, is also going to be a fugacity for non-singlets in the matrix model. And it's going to be related to the Z of the string theory. When ZB is 0, the integral over the twist basically makes sure that you only have states which are in the singlet sector of the PUN symmetry. But when ZB is not 0, you're allowed other states. This is our model. Okay. So now the question is, when we say we have, what is the free energy of the black hole? That's actually very hard to answer because it's a very stringy black hole. We don't actually know how to calculate the 1 by g string squared leading genus 0 term in the free energy of a black hole. So what Kazakov, and Tseytlin did was they calculated the partition function of the MQM using path integral techniques. Okay, and found some value for the genus 0 free energy. It doesn't particularly matter, except that notice that R equals 2 is special. And we are interested in R equals 3 over 2, which is less than R equals 2. So it's higher. There is some funny thing happening at a lower temperature than we care about. And if you want to look at R greater than 2, read Olga and Panis's paper, which also came out last week. Cool. And anyway, so Kazakov and Tseytlin basically found two different thermodynamic interpretations of this free energy. I won't tell you much about, I don't want to tell you anything about what the interpretations are, but there's one in the first interpretation, they subtracted off some divergence in some string theory divergence. Okay. And they interpreted Z as a coupling constant and interpreted the free energy as a canonical free energy. Okay. And when they did that, they got this guy, which vanishes at the temperature of interest, R equals 3 over 2. Okay. And they found this relationship between the entropy and the energy. Okay. In the second interpretation, they didn't do any subtractions. They just took this free energy at face value, considered it to be a grand canonical ensemble. So Z is a fugacity, not a coupling constant. And then they vary R. And then it looks very convenient when you exchange the grand canonical ensemble for the fixed charge ensemble. Go to a case where there are a fixed number of winding vortex anti-vortex pairs on the string, okay, which is this K. And they found a free energy, which again has something special at R equals 2. And notice that there's a concrete, very specific difference between these two interpretations, meaning that one of them is wrong, because it posits a relationship between entropy and energy, and the Hilbert space either has one relationship or the other. It's just a fact about the Hilbert space. So we will show that the second one is correct. And I won't talk about the first one at all. Okay, our main result is this, that we have this free energy from Kazakov and Tseytlin. So now there's 2 minus R, which means there's a phase transition at R equals 2 at some lower temperature. The leading bit is proportional to K, the number of pairs, and there's also log K behavior. And there is this UV cutoff. This UV cutoff was introduced based on some dimensional analysis. And then there is a uncertainty. Okay, which is the uncertainty is uncomfortably close to the K log K term. You know, K is just slightly smaller than K log K, but it is how it is. And then they didn't really have, Kazakov and Tseytlin did not give any value for the UV cutoff. We will find that this UV cutoff is N, the size of the matrix, and we will find the entropy and energy on the nose. In the regime where K is a big number, there's a lot of pairs, but does not scale as N in any way. Okay, so we will do it from a Hamiltonian calculation. What is the Hamiltonian calculation?
Ronak, sorry again. Can I ask a question about the uncertainty? So I guess, okay, if you just take the leading answer of the matrix model, you reproduce the first term, right? But I mean, you can get all the subleading corrections order by order. In principle, okay, it's hard to compute everything. So in some sense, this would fix also the later terms, disorder K, etc., right?
Oh, yeah, presumably. Actually, I don't remember. So there's a lot of renormalizations in this story, and
yeah,
it's a whole other thing to keep track of where they're coming in. So it could be that some renormalization effects are also popping up at order K. I don't know.
The precise numbers in front, yes, yeah, that's right. Okay.
Yeah. Okay, good. So now I will do a Hamiltonian calculation of the free energy. Good. And what do I mean by Hamiltonian calculation? I mean that I will look at some states, calculate some quantum states in the Hilbert space, calculate the energy, count them, right? And for that, we need to know about the Hilbert space. So let's start with there. So what is the Hilbert space? Our degree of freedom is a matrix. So the Hilbert space is a set of functions of the matrix. Okay. Now we can write X as U dagger lambda U, where lambda is a diagonal and U is a unitary. This is not quite a unique decomposition because you can reorder the eigenvalues and then you change unitary, you get the same X. So just for uniqueness, I will order the eigenvalues, say that the eigenvalues have to be in ascending order. And so then U is fixed uniquely. Okay. This is not necessary. You can like keep around some factors, and anyway, it's a whole thing. So Xij looks like this: U dagger Ik lambda K UKJ. So because of the decomposition, you can write any function of X as a sum of functions of the eigenvalues and a functions of the unitary, but not arbitrary functions of the unitary. Functions of the unitary where the unitary has to come in this combination, because this combination is what turns up in Xij, and Xij are the physical variables. Okay, so you have all functions of unitary are actually functions of U dagger Ik UKJ for different Ik and j. Okay, so it's like and by the way, the eigenvalues, because of measure factors, which anyone who studied matrices have learned about, become fermions. And so from now on, I treat them as fermions. One of the important things about this decomposition is that there's a symmetry. Under the symmetry, the eigenvalues don't change. So in particular, the eigenvalue wave function is also untouched by the symmetry. It only acts on the rotational wave functions. The last point is that under this decomposition, this Hamiltonian becomes eigenvalue Hamiltonian, which is n free fermions, and a rotational Hamiltonian. The rotational Hamiltonian has this tau KL, which I have not defined, and I will define that later. But notice that it has in eigenvalue space, there is some repulsion sort of thing going on. It diverges when lambda K and lambda L go very close by. Good. So now let me just tell you about the singlet sector, where the In the singlet sector, the rotational wave function is just a constant. The PUN acts as identity. It doesn't do anything. The state is just invariant, right? And so basically, there's only eigenvalues. And in the singlet, what happens is that you have fermionic eigenvalues. There's a lot of them. So you can just treat them semi-classically and say that each eigenvalue occupies a single cell in phase space. Then you have a Fermi C up to some Fermi energy. This is the Fermi energy. I'm calling the Fermi energy minus mu. And this is the, right. So you get what's called a phase space eigenvalue density, which just says that there is a eigenvalue in every cell whose energy is less than minus mu. Okay. And to get bulk string theory, you need to look at what's called the double scaling limit, where you take n to infinity, keeping mu constant. Mu is the Fermi energy. Okay. So mu is the thing that turns up here. Okay. It is what tells you the left edge of the distribution. And n is where it tells you where it stops on the right edge. Okay. And what we are saying is that we are sending n to infinity, which means that every eigenvalue to the right of this line here, the right of this line is filled. That is what the double scaling limit has. You can also integrate over the momentum to get a density in eigenvalue space, rho of lambda. Okay, which the important thing is that at large enough lambda is going to just look linear in lambda. Okay. This is kind of an interesting formula because you can ask the following question. Where is the eigenvalue corresponding to where is the ith eigenvalue? Remember the eigenvalues are ordered. So where is the ith eigenvalue? Where I equals 10, say. For that, you just can integrate rho of lambda from from 0 to lambda, and then it's an integral equation in this, sorry, rho of lambda, right? Yeah. Sorry, yes. So you just ask how to get the position of the ith eigenvalue, integrate rho of lambda and ask when it becomes equal to I. And this is what an eigenvalue density does for you. And yeah. Sorry, that was a bit of an aside. So bulk closed strings propagate on this Fermi surface. A bulk closed string is really just you form a hole and you excite one eigenvalue, and then it kind of goes here, hits, and then comes back. Okay, so this is what a bulk closed string does. And what you find is that this point here is lambda equals root 2 mu. And you find that because the S matrices in the bulk string theory are non-analytic in this mu parameter. This mu parameter is the same parameter that I mentioned in Sine-Gordon. Sine-Gordon theory, the mu e to the minus 2 phi term cut off the unstable direction of Liouville. Okay. So now let's look at there's a second way of thinking of double scaling limit, which is also very nice. Basically, it's the limit where the MQM Feynman diagrams have order of n faces. Okay, and you send n to infinity. When you send n to infinity and you have order n faces, you keep the area constant, it starts looking like a smooth manifold. So this is a Feynman diagram, and this becomes a string worldsheet in the limit, in the double scaling limit. Okay. So 1 by n is really a cutoff on the worldsheet, and that's why it appeared as like a cutoff in the Kazakov and Tseytlin result. They had some lambda, it becomes n. And it needs to vanish for string theory to emerge. Though this paper by Amar and Aaron that's upcoming will argue that you can keep 1 by n finite. So the important thing is that the MQM parameters are bare parameters on the Feynman diagram, which is latticey. And then the stringy parameters are renormalized parameters. And so, for example, the Z gets renormalized like this. You have to absorb some powers of n, which is the cutoff. And the vortex is just some phase that if it wraps around the circle, that's a vortex in the string theory. Good. So now let me get to the important part, which is the rotational wave functions. Let me stop here if anyone has questions for what I said till now. Okay. It's either a good sign or a bad sign. Anyway,
Maybe a question about this finite n thing.
mhm.
So the finite n cannot be related to the string theory on an allowable background, right? String theory, it should be related to something more of shell or something more.
Yeah, actually, I misrepresented the upcoming work. It's really just about off-shell string theory, which allows you to have a non-zero cutoff on the world sheet. And I just kind of said that 1 by n is also a cutoff. But yeah, they do think about off-shell string theory on off-shell backgrounds.
Okay.
Yeah. Good. So now let's look at the rotational sector. Now, as I mentioned, the simplest rotational wave function is this function of a unitary for some ijk. And every rotational wave function is made out of sums and products of these little elementary guys. Okay, for different ij's in case. And now there is a symmetric PUN action on the X, which acts on the unitary as U goes to UV. And if you just look at this elementary bit, you'll notice that the symmetry action only acts on the two outer indices I and J. It leaves the K untouched, right? Because yeah. Yeah. So there is, similarly, there's a left action, okay, where U goes to VU. This acts on K. And actually the actual action that, the actual group that acts from the left is UN left quotiented with U1 to the N. The reason it's left quotiented with U1 to the N is that U1 to the N is the set of diagonal unitaries. And if you act with the diagonal unitary, because the K indices are repeated, it's just phases that cancel. Okay. So, and the point is this U1 left quotient with U1 to the N is not a symmetry. And the generators of the corresponding Lie algebra are what appear in the Hamiltonian as this tau K L squared. Okay. Good. And we can also rewrite for various purposes, it's useful to rewrite this elementary wave function in this form. So I have split off the left action and the right action. Okay, because the left action acts only on the Ks, the right action acts on the I and J. I split them off into two different cats. Secondly, I have put these funny boxes. A white box is a fundamental of the UN. A green box is an anti-fundamental of the UN. Okay, these are the an empty white box is a representation. A white box with a letter inside it is a state in the fundamental. But similarly with anti-fundamental. And when you put those two boxes next to each other like that, you get the adjoint. Okay, it's a fundamental times an anti-fundamental has an adjoint in it, and this is the adjoint. And under both the right and the left actions, the most basic wave function is an adjoint. Okay, so the representation theory of PUN says that all the irreps that appear are those that appear in the products of the adjoint. So so in some sense, the fundamental wave representation for this action is actually the adjoint representation, which is a very confusing sentence, and I apologize for saying that. The important thing is that the left action has the same letter on the fundamental and the anti-fundamental. So if you think of an adjoint as a matrix, the left action is like a diagonal matrix. And this is just a general matrix. Okay. Cool. So now let's reproduce the entropy of Kazakov and Tseytlin in 2 lines. And by the way, sorry, I should just, I forgot to write here. This calculation was originally done by Kiros and Klebanov in 1990, which is the year before I was born. So it's a very old calculation. Yeah. So basically what you need to do is we need to go to the sector with K adjoints, where again we have this math BBK. Okay. So a particular sort of wave function in that sector has K of these pairs. Okay. And there is some wave function for the distribution over the inner indices, because the inner indices have a Hamiltonian, they participate in the Schrodinger equation. So when you look at an eigenstate, they're fixed. The outer indices don't participate in the Schrodinger equation. They can be anything you want. So really the number of states with the same energy is the number of outer indices you can put. But it doesn't matter where you put the outer indices, which pair you put outer indices in, right? Like there's some indistinguishability going on. You can just rename what is the first pair and what is the second pair. So it's like each outer index pair is an adjoint. And the fact that you can kind of rename things is the fact that these are indistinguishable adjoints. So the dimension of states is dimension of k copies of the adjoint mod the symmetric group of k, which is n to the 2k mod k factorial over k factorial, which is this, which is exponent of this. So the number of states is e to the kt entropy. Now, of course, this is a wrong calculation because k copies of the adjoint is not an irreducible representation of the PU symmetry. Only irreducible representations are guaranteed to be degenerate, not reducible ones. The reason it works is that k copies of the adjoint is dominated by one irrep. This is also found by Panos and Ulga. That irrep is drawn by the Young diagram here. Now, I don't know how much people know about Young diagram, so let me just spend 1 minute explaining this. So a Young diagram is a bunch of little boxes. So I did a very basic Young diagram earlier. And any two boxes, every box, white box is fundamental, every green box is an anti-fundamental, and any two boxes which appear in the same row are symmetrized, and any two boxes which appear in the same column are anti-symmetrized. Okay. And this guy is an, what is it? There are k boxes and k anti-boxes, right? K in each part of the diagram. And this is approximately an isosceles triangle. So the height of this guy is square root of k. There are square root k boxes in the square root k rows and square root k columns. Okay. I'm throwing away order one factor. So that's why my description of a triangle looks like a rectangle. Okay. Good. So now I will argue that this entropy is completely uninteresting. So as I mentioned, the string theory really comes from the continuum limit of Feynman diagrams. So let's look at a very simple Feynman diagrams. Feynman diagram with two vortices. You have just two faces on the Feynman diagram, face 1 and face 2, which is not pictured. It's on the other side. Each face wraps around the thermal circle. So you have a vortex and an anti-vortex. Now you cut the bit that goes through the t equals 0 slice. Okay, because there's a thermal circle and it's like an open string going around the thermal circle. And at the t equals 0 slice, you find some matrix element xij. Okay, which you can decompose like this. Now, since every index I has an eigenvalue attached to it, you can ask where is the ith eigenvalue. I told you how to do that calculation earlier in a very awkward manner, but there is some calculation you can do. Okay, so the answer is that lambda I is always at 2 pi I. Okay, so there's an answer to where is the ith eigenvalue always. So you can think of this little line as going from lambda I, okay, because there's x, right, going from lambda I to lambda k is what's in the middle here, and going back to lambda j. Oh, I realized that I flipped the color schemes. I'm sorry. Anyway, the green and the red, the I and j got flipped somewhere. Oh no. Yeah, there's some inconsistency in the picture. Anyway, the point is that you could think of this line that's passing through t equals 0 as a string that goes from lambda I to lambda k and then back to lambda j. Okay. This guy, the position of this, the string tip carries energy. This carries entropy. Okay. Why do I say that? Well, because we just calculate the entropy by asking where all the outer indices on the U's could be. which are literally the outer ends of the string. Okay. And the point is that the position of these don't really participate in the energetics, which means that they can be anywhere. And most things because I ranges from 1 to n, most possibilities are order n. Okay. And order n means infinitely far away. So the entropy is counting how many places these open strings can end off at infinity. Okay, so it's some IR degree of freedom that's completely uninteresting. It's at infinite distance from all interesting physics. Okay, so this is why I think we think the KT entropy should not be considered an entropy of the black hole. Okay, was that? Yeah.
Ronak, just a question to see if I understood. So is it clear why lambda and lambda j should be on the right of lambda k?
In this, I know why you're asking that picture and question, and we have thought about this. And so from our point of view, basically lambda k is kept to some order one number by dynamics, and lambda I, lambda j are order n generically. So typically you expect them to go all the way off. You, of course, have stress strings that come from the other side, where lambda and lambda j are to the left. And I don't know what's going on there. That's something that we've been discussing on from our side as well. Like, yeah. Thanks, yeah. Anyway, cool. So anyway, so this is the point. Great. So now we come to the interesting bit, which is the state, the specific state that solves the Schrodinger equation and is a black hole-like state. Okay, we call it the hole in the world state. And I have drawn it here. So now let's take a moment to go over the diagram. So the outlines are this is a Fermi sea. And so is this. Okay. So everything inside the outline is a Fermi sea. It's like where there are non-zero eigenvalues. So rho of lambda is plotted. And notice that the Fermi sea has 2 bits disconnected from each other. Unlike the previous case, where the Fermi sea had only 1 bit. Yeah. Here, the Fermi sea has only 1 bit. Okay. Here, we've blown up a hole in the Fermi sea. And we call it a hole in the world because the Fermi sea, in some sense, forms the spatial direction of Liouville, of the bulk theory, up to a non-local transformation. Good. And this little bit has nu of order root k eigenvalues. Okay. So because there's nu of order root k eigenvalues, this is the edge is at lambda equals k to the 1/4 because there's a square root between the eigenvalue number and the eigenvalue itself. Okay. And what are the colorings? I mentioned earlier that the string tips are associated to some eigenvalue. The coloring means that there are string tips attached to all of these eigenvalues to the left. Okay, there are no string tips attached to the guys on the right. Okay. This is almost complete description of the state. The only thing I need to tell you is what the wave function of the string tips is. And the wave function of the string tips is written here. Okay. This part might be a bit opaque, so let me spend a minute on it. So first you have a single adjoint. This is an adjoint state. Okay. And this is adjoint state. We have taken a superposition over the string tip being at every position, every eigenvalue from the first to the nth. Okay. K has from 1 to nu with equal weights. What this does is it makes this guy a singlet under U of nu. Okay, because whenever you take a fundamental and anti-fundamental, you can make a singlet by tracing over them. By tracing over them, like psi bar psi or something, or phi by phi. But this is not a full trace, a trace over some part of the Hilbert space, but some part of the fundamental space from 1 to nu. So it's a U nu singlet, but not a UN singlet. It's also a UN minus nu singlet because it doesn't have, it's basically like, it's something that only has stuff at nu and it's just 0 from over n minus nu. And so clearly, you should consider matrices acting on this. All matrices, a matrix that is 0 here, here, and here has a trivial action on this vector. Right. So the only interesting part of the matrices are here and here that have an interesting action on the state. Okay. And you take k copies of that because there are k adjoints. And that is the wave function of the string tips or the adjoints. If you didn't follow the argument for why it's a U nu cross UN minus nu singlet, don't worry about it too much. It's a fairly simple thing which I'm not explaining well. Okay. Right. And then the last question is, why is nu of order root k? Well, if nu was smaller than order root k, remember that the dominant irrep had root k rows in the Young diagram. And each row is anti-symmetrized. So you have to have at least square root k distinct states in the space you're looking at. So if you try to squash nu to a smaller value, you'll basically get find a cutoff guy like this, which Olga and Panos do find in the low temperature phase, which we don't consider. But we want to allow the dominant irrep to turn up, so we allow nu to be root k. Of course, it could be bigger, but it turns out that when you make it bigger, the energy increases. So this is a sweet spot where you allow the dominant irrep, but don't allow too much energy. So, okay. So now let me give a little more detail. So the state is a U nu cross UN minus U singlet. What this means is that tau KL less than nu annihilate the state. Similarly, tau KL greater than nu also annihilate the state. Because these are the generators of U nu. These are the generators of UN minus nu. The only guys that don't annihilate the state are tau KL, K less than nu, L greater than nu. They're the only ones that don't. And the Hamiltonian, remember, had these tau KLs. Where is the Hamiltonian? Here. So the only ones that survive are where lambda K is less than, is in the left blob, and lambda L is in the right blob. And it turns out that you can show that tau KL squared is 1 for all of these cases. So the energy is just a sum over the non-singlet part of the energy is just this, where all the tau KLs have been set to 1 in the case when K is less than nu and L is greater than nu. Okay, so these correspond to virtual processes where a string tip jumps out and comes back in. Anyway, there's some integrals. I just wanted to show you the simplicity of the calculation here. The point is you get this integral, and this integral has a log divergence. Okay, and so this a log is interesting because it has a divergence of the IR as well as the UV. So the IR part gives the n gives an n log n, and the UV part gives the distance between the closest colored and uncolored eigenvalues. Okay, in this case, the distance is order k to the 1/4. But if you didn't blow up this hole, the distance would be really small. Okay, so you would have a lot of energy from the UV divergence. What this hole is doing is it's regulating this UV divergence. So in some sense, you basically form this little singlet of UNU, and then the back reaction blows up a hole. But now that we've blown up the hole and the minimum distance is large, you get a low energy. And you get exactly the KT value of the energy. And of course, I did not say that this is an eigenstate. So you can check the variance in the energy, and it's basically just if this was lambda minus lambda prime squared, this is lambda minus lambda prime to the 4, and you find that it's root k, which is much less than the square of the energy, which means that the variance is really small and it's an approximate eigenstate. Now, this because not an exact eigenstate, it kind of evaporates. Not only is it not an eigenstate, it's also not like a very low energy state. You can send all of the string tips off to infinity and make a very small energy state. But that possibility is always there. So it's not stable, it is metastable. But the point is it evaporates slowly. How does it evaporate? It evaporates by one string tip jumping out. Okay. And then there's a simple enough calculation you can do to find that the evaporation time is like k to the 7/4, which is of course much bigger than the mass. Yeah. It's not usually good practice to compare times and masses, but there are dimensional factors that make sure it works. Okay. Cool. So we can see that it evaporates slowly. So this is the hole in the world state, and this is what dominates the partition function, the double scaling limit. For this, basically, as I mentioned, there are states where you can send all the string steps to infinity, and they have lower energy, so technically they should dominate the partition function. But there is some implicit subtraction procedure where we throw all of those guys away. Okay, only keep states where the string tips are at finite distance. And when you only keep those states, this guy does dominate because it has very low energy compared to other states. So this is the explicit description of the black hole microstate. Okay. So now there's a discussion section. So let me stop for questions. All right, there's no questions. So now let me just emphasize some things that I've said partly, but I want to say again. So it's the hole in the world state is an explicit quantum mechanical black hole microstate. So let me tell you about all the properties that make it resemble an asymptotically flat black hole. It is a bound state of many non-singlets. Okay, like if you have the analogous thing is that if you have a shell, there's a non-bound state which is just a shell, but there is a bound state where you have a black hole. Okay. The non-bound state kind of to have a non-bound state, you require the adjoints to be spread out over a region in lambda space of order root k, which is much bigger than the k to the 1/4 that the hole in the world lives in. So in some sense, you need to like really spread out all the non-singlets to have them not collapse. So there's like an effective Schwarzschild radius. Okay. It is, of course, it is metastable and evaporates slowly, which is the asymptotically flat part, as Panos emphasized earlier. Interestingly, if you take n much less than e to the k, which is of course not nice from the string theory side, but something you can do on the black hole side, it's a bit like putting the black hole in the box. Okay, and when you do that, when you put the black hole in the box, it becomes stable. It's just like an ADS black hole. And then you can actually look at the excitation spectrum of this hole in the world state. We did some estimates in our paper, And we argued that it kind of looks like the spectrum of sine-Liouville theory. Okay. A small final word on entropy. As I mentioned, the KT entropy kind of counts in uninteresting higher degrees of freedom. And mathematically, you can see it as basically that the entropy renormalizes the fugacity. So I mentioned that the MQM fugacity and the bulk fugacity had this renormalization. And the entropy exactly does this renormalization. Okay. So you might think that the entropy is zero because there's just one state I described. But in some sense, there is still some entropy which you should consider, which is that when you take K adjoints, there is a permutation symmetry. It doesn't matter what order you took the adjoints in. And this also turns up mathematically when you calculate the partition function. So you should really think of the black hole as coming from K adjoints rather than from some. If you think about it in terms as coming from K adjoints, and then there is a entropy which is log of the size of the permutation group, which is K factorial. So we think that the black hole entropy should be considered to be K log K. Okay, this is not a terribly. This argument is not on terribly good footing, but this is our belief. This is how we think it should be countered. Now, finally, relevance for less finicky black holes, which are in high dimensions. So many high dimensional black holes, as again Panos pointed out earlier, have a sector with a cigar factor, but when K is greater than 3. Okay, so like at lower temperatures. The FZZ duality still exists, so the cigar is still dual to some sine-Liouville CFT, but it's some C not equal to 26 CFT. And basically what breaks when you do that is that, where's the picture? This part doesn't generalize. Okay, the bottom line. The top line still exists. So we don't have an MQM description in general for these high dimensional black holes, which makes sense because it's a one matrix quantum mechanics. There shouldn't be too much in there. There's only so much stuff that you can stuff in one matrix. But we still do have the sine-Liouville theory. And what we believe is that our solution says something interesting about sine-Liouville theory on its own term. It says that you have these open strings, these stretched strings that Maldacena spoke about. Okay. And the state you should look at is the one where the stretched strings kind of collapse into this bound state. Okay. And we believe this should generalize to sine-Liouville theory at other temperatures as well. We don't have a very precise description of this, but we think that in this way, our work could form some sort of preliminary basis to understand microstates even in high dimensional black holes. So, conclusion, we found an explicit black hole-like state in the matrix quantum mechanics, which I have drawn for you here. And it has some black hole-like properties. I think it's really to my knowledge, the first time there is a state with such explicitly black hole-like properties in quantum mechanics. So future direction, of course, is understand the sine-Liouville better. Try to make a bulk calculation in the cigar using the off-shell stuff that Amar and Aaron are working on. Can we calculate the entanglement across some cut in the bulk? We had some brief discussions a few months ago with Sean Hutnall. And finally, I had this recent paper with Eva Silverstein and others where we took some black hole microstates and mapped them to microstates of a cosmic horizon in de Sitter. And the natural question is, can one do that with these microstates as well, using TT bar deformations and so on? Yes, that's it. Thanks a lot.
A lot for the nice talk. Any questions for Ronak?
Yeah, maybe I'll just ask a clarification. So you had shown the estimate of the black hole or some lifetime,
Yeah.
the evaporation time. Yeah, so yeah, I was wondering if, is that something that you have an independent calculation for in two different pictures, or this is just from the matrix side? And
no, we have no, the only calculation of this is literally the picture I've drawn. So yeah, it's not like we are.
Do you think there could be some other way from the bulk? Or, yeah.
I think we had some brief discussion about whether there was a bulk calculation, and we do not know of any, and we don't know how to set it up as well.
Okay. Okay.
But it would be definitely be an important thing to verify whether this can be verified from the bulk. Also it's a very rough estimate, so maybe there's some way to make it better.
Yeah. Thanks.
Yeah, I think the importance of this is just that it's long-lived, not that it like at this point there is no clear importance to the actual value.
So Ronak, if I understand correctly, your picture is similar to the Saska and Uglum picture, right? So in some sense you have all these tips of strings, and I mean, can you understand more or less where the horizon would be? Is it related to the presence of this gap? The eigenvalue density and the tips are somehow related.
I don't want to make any claims over the horizon, but I can tell you something interesting, which is that in sine Liouville there is a potential that from the sine Liouville term, and basically it blows up exactly at this point. So all of this is behind the wall.
Okay, and this brings me, we have discussed this again, but Joanna is also here. So Joanna had a paper with Andy Strominger about some cosmologies, let's say, in this matrix quantum mechanics, and they were also related to some compact, let's say, eigenvalue densities that were evolving. Have you thought about the connection with that, or can you say how this, how this, I don't know what color is it, this blob would evolve, let's say, in time, or because this is a kind of like static picture, right?
Yeah, actually, I know Alex has read that paper and thought about it, so I'll give this question to him.
No, I've not yet read that paper closely enough to have anything concrete to say on the topic.
Yeah.
But yeah, we can call that a work in progress.
Hi, you guys can hear me.
Hi, yeah.
Yes.
Yeah, so, I mean, your eigenvalues are going to be, right, our eigenvalues would evolve along that hyperbola. Those are going to not really doing that, right? Because they're stuck due to the interactions with the tips.
Yeah. Yeah, it doesn't. The only way it evolves is by jumping out. Actually, it doesn't.
Right. So it's a very different picture, right? Our eigenvalues simply floated along the hyperbola using the free equations of motion.
Yeah.
But
Diana, you also had some compact cosmology, right? You had two types of solutions. One of that were non-compact.
Yeah, no, but
like
they were still, they were compact. They were definitely compact things, but they would just
slide the equations.
They were still, because we were in the singlet sector, they were still, those compact droplets were still made out of eigenvalues which evolved according to the free equations of motion. So they would very quickly, basically fall down the hill, if you will, down the minus x squared potential hill. These are very different, right? Because they are supported by this whole interaction with non-singlets. And okay, I understand they're not static, right? The black hole is evaporating,
but they evolve very slowly, like tunneling.
So I don't know what, if any. But I do have a question actually. Can something fall into this black hole?
Yeah. So a singlet, basically. So this is something that So a singlet, which is a whole particle pair, reflects off the wall here. Okay. And this is all in agreement with some sign level expectations. But a non-singlet, I have a picture there. Here. A non-singlet, when it tries to go, it kind of jumps in. So basically non-singlets kind of fall into the black hole. And then they evaporate.
But singlets can't. So you can't just literally say, oh, there's some energy coming from infinity, it will fall into the black hole.
Yeah, not an arbitrary energy. That's right. Singlets have a small tunneling potential to go across the hole, but
Right.
almost all of it kind of comes back out.
So basically, we had this picture, we had this paper also called something like the non-formation of black holes. That's
Right,
probably all still holding here. I mean,
Yeah,
at the
exactly.
classical level. Yeah.
Yeah, definitely.
Thank you.
Yeah, sorry, I didn't mention that paper, but
No, it's fine. I just trying to understand how that fits in. Very old work.
yeah.
Not quite as old as you are, but still.
Yeah.
I would say it's still important that singlets do have a non-zero probability for tunneling through, because I mean there should be some inverse process to the singlets that are tunneling out to begin with.
Yeah, no, that's for sure. And I think it's in contrast to if you're completely in the singlet sector, they have nowhere to go, so they can't tunnel in because there's nowhere to tunnel into.
Yeah.
Now, I did also want to say that inside the disconnected region, the fermions are still free in some sense. It's really two different. It's really two different compact distribute or I guess the right one is not compact, but two different distributions of free fermions that only interact with each other across the board.
Yeah. This singlet thing that we did make sure that everything the blob is free. Yeah.
Any other questions for Ronak?
Just on one very quick question. I don't know if it makes any sense, but there are these people that have discussed about this partial deconfinement, right? Which is some kind of like similar structure because the full gauge group in your case was split into a u little n part times un minus little n, right? And this was relevant, I think, in ADS for the black holes that can actually evaporate.
I see.
Yeah, I don't know if you have thought about any relation to that, but okay, I don't know. Just
Okay, no, we haven't started like
okay. Anyway, thank you.
Yeah.
Okay, let's thank Ronak again.
Thank you. Yeah.